Hi guys, Miss O'Connell here. So I just need to get through the last two examples that we hadn't gotten to in class the other day. Okay, so this video is about finding impulse from a force versus time graph. Okay, so it's example number 7 and example number 8 from the first set of guided notes, which are called momentum/impulse guided notes. Okay, so let's get started. Okay, so for example number 7, we have a force versus time graph, and we're asked to find the impulse. When we're given a force versus time graph, we can find the impulse by taking the area underneath the curve. Okay, and why this works is actually related to calculus, which I know that we have not yet learned, but technically, if the force is not constant, which in this case it is not, when the force changes or varies with time, the impulse will also vary as force varies over that time interval. Okay, so in calculus, we use a lowercase d to show a change. Typically in algebra or in AP Physics 1, we'd be using a delta symbol. Okay, so our impulse would be the integral of some force as a function of time, and we would determine that change in terms of time. Okay, so basically we would determine how the force changes during two different time intervals. Okay, we're not given an equation here, and we're not expected to find the integral, but the integral is the same as taking the area under a curve. Okay, so we're going to take the area underneath a force versus time graph anytime the force is not constant. So we see that force changes or varies over time. We would take the area under that curve or below that curve to find the impulse, J. Okay, so let's give this a try. So you want the impulse of the entire graph, which means the entire time period. So the problem, if we were given a word problem, would most likely say, find the impulse from t equals 0 to t equals 7 seconds. So what we would do here is we'd find the area underneath this force versus time graph from t equals 0 to t equals 7 seconds. So what we want to do is break the graph into shapes in which we could easily find the area. So I'm going to call from 1 second, we'll call this A1 for area 1. Okay, from 1 to 3 seconds will be area 3, that looks like a square. We have another triangle over here, we'll call that area 3. Whoops, there should be area 2. Please fix that. So we have area 1, area 2, area 3. And then technically here, below our curve, we also have an area. Okay, so we're taking the area between the curve and the x-axis. So I'm going to call this area 4. Notice here that the force is negative here. So that means the impulse will be negative. Impulse is a vector, just like force. So when we find the area, we're going to have to subtract this negative portion from the positive portion. So I start out by finding J, which is equal to area. So J, our impulse, we're going to take area above the curve or above the x-axis and subtract the area below the x-axis. Because at that portion, the impulse will be negative. Okay, so let's give it a shot. So I have impulse is equal to, it's going to be A1 plus A2 plus A3 minus A4. We need to calculate the areas at those specific time periods. So I'm going to start out going to write my equation right down here so I have a little bit more room. Area 1 is a triangle, so I'm going to have 1/2 times the base times the height. My base is 1 second, and my height is 6 newtons. Right, so I have 1 times 6, I get 6 Newton seconds. 6 times 1/2, I'm going to get 3 Newton seconds. Right, so the units there work out as well. When we're taking the area, we get the same units we would for impulse. Okay, so I plugged in for A1. Now we're going to head to A2. We have base times height. My base, I'm going to have 3 minus 1. So this length is technically 2, and my height is still 6. So I'm going to have 2 seconds times 6 newtons. I get 12 Newton seconds. It's above the x-axis, so I'm going to add that area. Next up, we have A3, which is again is 1/2 base times height. My base is going to be 5 minus 3, I get 2, and my height is still 6 newtons. So I'm going to have 12, 6 times 2, I get 12, divided by 2, I'm going to get 6. So I have 6 Newton seconds. So I'm going to add 6 Newton seconds in my next line here. Finally, A4, we're subtracting that area. It's below the x-axis. It again is a triangle. So I'm going to take 1/2. The base of my triangle, which here is going to be 7 minus 5, I get 2 again. And my force this time, the force is 2 newtons. Okay, so because we're subtracting, we're taking care of that negative sign here. Okay, because we're subtracting this. Okay, so I'm going to have 2 times 2, I get 4. 4 divided by 2, I get 2 Newton seconds. And now we just simplify to find the impulse. 3 plus 12, I get 15. 15 plus 6, I get 21. And then 21 minus 2, I'm going to get 19. So my impulse here is 19 Newton seconds. Okay, if we were asked for change in momentum, what would the change in momentum be? The same. Okay, so impulse is equal to change in momentum. So we can actually use these graphs as well to find change in momentum if we needed to, because change in momentum and impulse are equal to each other. All right, let's try one more. So in example 8, we have a 5 kilogram object with an initial velocity of 3 meters per second experiences the force shown in the graph. What is the velocity at 6 seconds? Okay, so we have a force that is not constant, it is changing over time. So if our force changes over time, our impulse is going to change over that time. So we need to take the area underneath the force versus time graph to find out what the impulse is. In the problem, we're asked for the velocity, given the mass and the initial velocity, and we specifically want the velocity at 6 seconds. We know that impulse is going to be equal to the change in momentum. So if we can find the impulse, we can find the final velocity of the object using the impulse momentum theorem. What we specifically need is the impulse when the object reaches 6 seconds. So I'm going to identify on my graph the force at 6 seconds. I want the area underneath the curve from 0 to 6 seconds. So I need to take the area under this curve to find the impulse from 0 to 6 seconds. We can see here, right? We can break this into 2 easy to model shapes. So I have one triangle here, which I'll call area 1, and I have a rectangle here, which we'll call area 2. So our first step here is to find the impulse. And I'm going to do that right on the graph, actually. So impulse is going to be equal to area 1 plus area 2. So I have 1/2 the base, which in this case is going to be 3 seconds, times the height, which is 30 newtons. Okay, so we simplify that. I'm going to get 3 times 3, we get 9. So I have 90, half of 90, we get 45 Newton seconds for area 1. And we're going to add area 2, which will be base times height for our rectangle. Our base is 6 minus 3, so that means that our base is 3 seconds. And our height is, again, 30 newtons. So I'm going to get 90 Newton seconds. For a total of 135 Newton seconds. So that is our impulse. Great. So the impulse experienced by the object from 0 to 6 seconds is 135 Newton seconds. This object we know is 5 meters. It starts out with an initial velocity 3, and we need the final velocity. We also know that impulse is equal to change in momentum. So we're going to use that theorem to determine what impulse is. So I have impulse J. I know change in momentum is mass times final velocity minus the mass times the initial velocity. So I'm going to plug in for my impulse 135 Newton seconds. Will be equal to 5 kilograms times the final velocity, which we are trying to find, so we'll leave as a variable, minus, again, 5 kilograms times 3 kilogram meters per second. Sorry, times 3 meters per second. We multiply those two, we'll get 15 kilogram meters per second. Okay, so I'm going to take 15 and add it to both sides of the equation. We get 150 Newton seconds is equal to 5 kilograms times V final. I'll divide both sides of the equation by 5 kilograms to get V final by itself. And we find that the final velocity of the object will be 30 meters per second. Okay, and that's it. So just real quick for the homework, originally what was assigned was 1, 2, 4, and 9. The problems that you can do are actually 1, 2, 5, and 9. So make sure you give 1, 2, 5, and 9 on homework 2 a try over the weekend over the weekend. See you guys on Monday. Have a great rest of your day.